Attention is all you need. Today we will talk about attention mechanisms. Okay, let's start. Attention mechanisms came out of a very practical problem, and we had sequence models that were trying to sequence an entire sentence or an image or an studio clip into a single fixed size vector. And the obvious question is, why force a model to remember everything equally? That's not how we reason. When we generate an output, we selectively care about different parts of the input at different times. Attention formalizes that idea in a way a neural network can learn. Okay, so here's the core idea. When the model is about to produce one output element, it pauses and asks a very specific question. Which parts of the input matter right now? It then assigns higher weights to those parts and lower weights to the rest. Those weights are learned end-to-end from data. There is no manual rule here. The model figures it out. And let's put this in historical context. First, here in 2014, Batlano and colleagues introduced attention in neural machine translation. Before this, encoder-decoder models had a single bottleneck vector, and what they showed was simple but powerful. Instead of compressing the whole source sentence once, you can align each output word with different source words dynamically. That alignment is exactly attention. So, a year later, Long and collaborators refined this idea. They explored different ways to compute the alignment score. Some versions looked at all source positions, others focused locally. This work made attention more flexible and easier to plug into existing systems. And then in 2017, everything changed. Vaswani and colleagues proposed the transformer. The key move was removing recurrence entirely and using self-attention everywhere. Now each token can directly interact with every other token in the sequence. No hidden state chain, just direct connections. From there, things scaled fast. Bart showed how bidirectional attention works for understanding. GPT showed how causal attention works for generation, and vision transformers took the same idea to images. Different domains, same underlying mechanism. And if you look across this timeline, you can see a pattern. And what is that? Early attention helped sequence-to-sequence models survive. Transformer attention made scaling straightforward, larger models, more data, more compute, and the architecture stayed conceptually the same. So, why does this matter in practice? First, long-range dependencies. Traditional RNNs struggle when important information is far away in the sequence. Attention creates a direct path between any two positions. Second, parallelism. Since attention doesn't rely on sequential hidden states, you can compute everything in parallel. Training becomes much faster toward interpretability, and those attention weights tell you which input influenced a decision. And here, flexibility, the same mechanisms works for text, image, audio, or combinations of them. And scalability, of course, another important thing, and impact is here. You can see like GPT-4, DALL-E, AlphaFold, and other things. Okay, let's continue. And math. All right. Let's slow down and look at the math because this is where attention becomes concrete. And formally, attention maps a query and a set of key value pairs to an output. Think of the query as the question being asked. The keys describe what information is available. and the keys describe what is information is available, and the values contain actual content. The output is a weighted sum of the values where the weights depend on how well the query matches each key. Okay, and attention of q k v equals the sum over I of alpha of q and k sub I times v sub I. Alpha is alpha. This alpha term is the attention weight. It tells us how much the query q cares about k sub I. If alpha is large, that value contributes more to the output. At transformers, we usually use scaled dot product attention. The equation is here. Attention qkv equals softmax of qk transpose divided by square root of d sub k divides times v here. So here square root of d sub k is square root of dk, and here qk transpose is a matrix of dot products between queries and keys. Okay, and why this matters? I mean, why we divide y square root of d sub k? Because as dimension grows, dot products can become very large in magnitude. Large values push the softmax into regions with tiny gradients. Scaling keeps the numbers in a reasonable range so training stays stable. Look at the diagram. And here we see a computation flow. We start with q key and v tensors. We compute q key transpose, which gives us a score for every query key pair. Then we scale by square root of d sub k. Next, we apply softmax and converting scores into probabilities that sum to 1 along each row. Finally, we multiply by v to get a weighted sum. The output has the same sequence length and dimensionality as the values. Okay, we can continue, and here we will unpack these step by step. First, we compute attention scores using the dot product. The score of q and k sub I equals q dot k sub I. Dot product here just means element-wise multiply and sum. Second, we scale those scores by dividing by square root of d sub k. Third, we apply softmax. Alpha sub I equals e to the score I divided by the sum over j of e to the score j. That converts raw scores into normalized weights. And fourth, we compute the weighted sum. Output equals the sum over I of alpha sub I times v sub I. Okay, and let's make this tangible with numbers. Suppose d sub k equals 4. The query is 1, 0, 1, 0. The keys are 3 vectors: 1, 0, 0, 0, 0, 1, 0, 1, and 1, 0, 1, 0. The values are two-dimensional vectors: 0.5, 0.3, 0.8, 0.1, and 0.2, 0.9. Okay, we take dot products between the query and each key. That gives scores of 1, 0, and 2. We scale those scores dividing by square root of 4, which is 2, gives 0.5, 0, and 1. We apply softmax. That produces weights approximately 0.241, 0.146, and 0.613. And we compute the weighted sum of two values, multiply each value vector by its weight, and add them up. The output becomes approximately 0.289, 0.625, as you can see here. Okay, here scaling, and at this point the dot product itself is not a mystery anymore. The real question is why we divide by the square root of d sub k. Here's the intuition. As dimensionality grows, dot products between random vectors naturally grow in magnitude. Larger magnitudes push the softmax into extreme regions where one entry dominates and everything else collapses towards zero. When that happens, gradients shrink, learning slows down, and training becomes unstable. Dividing by square root of d sub k, pronounced square root of d k, risks those scores, so their variance stays roughly around 1. That keeps the softmax in a healthy operating range. And if you skip this scaling step, scores explode, softmax saturates early, and gradients vanish. Tuning becomes fragile. With scaling here, scores stay normalized, softmax outputs remain balanced, and gradients flow cleanly. This single division looks small, but it's one of the reasons transformers train reliably at scale. And here we have a table. Now, dot product attention is not the only way to compute these scores. There are several alternatives, and each one reflects a different design choice. The simplest is the raw dot product, Q transpose K, and it's fast and parameter free, but it assumes queries and keys live in the same space. Scaled dot product just adds the normalization term and is what transformers use by default. Additive attention, sometimes called Bahtinov attention, uses a small neural network with a 10H nonlinearity. That's okay, and it is more flexible and works even when dimensions differ, but it's computationally heavier. Multiplicative attention associated with long inserts a long weight matrix between Q and K, and cosine similarity normalizes by vector norms, focusing purely on angular similarity. Different tools, same goal, produce a meaningful compatibility score. Okay. Now, let's shift gears to self-attention. Self-attention is simply attention applied within a single sequence. Queries, keys, and values all come from the same source. That means every position can directly interact with every other position, no matter how far apart they are. And look at that box. The key consequence is that long-range dependencies stop being a special case. Every token has a direct path to every other token. There is no need to hop step by step through time as with RNNs. Yes, and we have a diagram. And take this sentence shown here. When the model processes the word cat, attention lets it look at the entire sentence at once. It can assign higher weight to related words and lower weight elsewhere. The output token for cat becomes context aware, not just a standalone embedding. Okay. And now, how do we actually get queries, keys, and values? We don't store them explicitly in the output. In the input, not output. Instead, we learn them. For an input sequence X, we compute Q equals X, W sub Q, K equals X, W sub K, and V equals X, W sub V. And W sub Q, W sub K, and W sub V are learned parameter matrices. These are linear projections, but they serve different roles. And queries represent what each position is looking for, keys represent what each position offers for matching, values contain the information that actually gets passed forward. The model learns to separate these rows because Doing so gives it more expressive control. Now comes the next question. Why stop at one attention operation? This is where multi-head attention enters. Instead of computing attention once, we compute it multiple times in parallel, each time with different learned projections. And the equation here is multi-heads of QKV equals concat of head 1 to head H multiplied by W sub O. Each head is its own attention computation, attention of QW sub I superscript Q, QW sub I superscript K, and VW sub I superscript V. And usually you can think of these as splitting the model dimension into several smaller subspaces. Each head runs scaled product attention independently. Then we concatenate the results and apply a final linear projection to mix everything back together. Okay, so why do this? A single attention head can only focus on the pattern at a time. With multiple heads, the model can attend to different relationships simultaneously. One head might focus on syntactic structure, another might track semantic similarity, another might focus on nearby tokens. Together, they give the model a richer representation. And importantly, this doesn't blow up computation. If the model dimension is D model and we use H heads, each head operates one dimension D, operates on a dimension D and a model divided by H. For example, in common BERT or GPT configurations, D model is 768, H is 12, and each head works with D sub k equal to 64. The total computation stays roughly the same. Okay, and when researchers analyze trained transformers, they often find that different heads specialize naturally. Some focus on local context, others on long-range dependencies, and others align with task-specific signals. This specialization is not hard-coded, it emerges from training. Some inside bugs, but look at that, some considerations. A few practical points here. Even though we use multiple heads, the total number of parameters stays comparable to single head attention because of dimension splitting. All heads are computed in parallel, which maps cleanly onto GPUs and TPUs. Dropout is often applied to attention weights to regularize training, and after concatenation, a final linear projection lets the model combine information across heads. Okay, let's continue. And architect, okay. Yes. Now, let's pull all the pieces together and look at the full transformer architecture. So, this model was introduced in the paper Attention is All You Need in 2017, and the key decision was radical at the time. No recurrence, no convolutions, everything is buried on attention. Once you accept that choice, the rest of the design starts to make a lot of sense. Start at the top. Look at here. We take the input tokens, convert them into embeddings, and immediately add positional encoding. That addition is important because attention alone has no built-in sense of order. After that, the data flows into multi-head self-attention. This is where every token looks at every other token and builds context-aware representations. The output of that block doesn't go straight onward. Instead, we apply a residual connection and layer normalization. Then we pass the result through a feed-forward network, followed again by another add and normalize step. What comes out is the output of one encoder block. Okay, and let's slow that down and go through each component in isolation. First, input embedding plus positional encoding. The embedding turns discrete tokens into dense vectors. The positional encoding injects information about where each token lies in the sequence. Without it, the model will treat sequences as unordered sets. Next comes multi-head self-attention. Each position attends to all positions in the previous layer. This is the mechanism that builds global context in a single step. Then we had add and normalize here. The residual connection literally adds the original input back to the attention output, and layer normalization resecures the activations. This pattern repeats again after the feed-forward network, which applies the same small neural network independently to every position. Okay, I'll continue. And let's talk about positional encoding in more detail, because this often feels unintuitive at first. Since the transformer has no recurrence or convolution, it has no natural way to know that one token comes before another. Positional encodings solve this by adding a deterministic signal to each embedding. Okay, so here the formulas shown here, the sinusoidal positional encodings. PE of pos, comma, 2i equals sine of pos divided by 10,000 to the power 2i over d model. PE of pos, comma, 2i plus 1 equals cosine of pos divided by 10,000 to the power 2i over d model. Sine is pronounced sine, from math. And each dimension corresponds to sinusoid with a different frequency. And we have a little box. Why use sine and cosine? Because this structure gives every position a unique encoding, allows the model to reason about relative positions through linear operations, and generalizes to sequence lengths longer than what the model saw during training. That last property turns out to be extremely useful. Okay, if you look at this visualization, each row corresponds to a dimension and each column a position. Lower dimensions vary slowly, higher dimensions oscillate faster. Together, they form a rich positional signal. And FFN. So the feed forward network inside each transformer block. So this part is deceptively simple. It's applied independently to every position. And the equation is FFN of x equals max of 0 at xw1 plus b1 multiplied by w2 plus b2. Max of 0 is the value activation, pronounced ReLU, okay? And even though this network is small, its inner dimension is typically 4 times larger than the model dimension. That expansion gives the model significant representational capacity. Alright. Now let's talk about two components that quietly make training work, and residual connections and layer normalization. Each sublayer, whether it's attention or feed forward, it's wrapped in a residual connection. The formula here is output equals layer norm of x plus sublayer of x. This creates a drag path for gradients to flow backward and allows the model to refine representations incrementally instead of relearning everything from scratch at each layer. And layer normalization itself is defined as ln of x equals gamma times x minus mu divided by sigma plus beta. So it normalizes across the feature dimension, keeping activation scales consistent and stabilizing training. Okay. The original transformer is an encoder-decoder architecture designed for sequence-to-sequence tasks like translation. The encoder stack processes the input sequence and builds contextual representations. It consists of n identical layers, often 6, with bidirectional self-attention. That means every position can attend to every other position in the input. Okay. And the decoder stack generates the output sequence one token at a time. Each decoder layer has 3 sublayers: masked self-attention, encoder-decoder attention, and a feed-forward network. The key difference here is masking. And in the decoder, self-attention is masked so that a position cannot attend to future positions. The mask is defined as mask ij equals negative infinity if j is greater than I, otherwise 0. Negative infinity is pronounced negative infinity here, and this mask is applied before softmaxed. So those entries become 0 probability. The result is causal attention, which ensures predictions depend only on known outputs. So yes, here, over time, researchers adapted this architecture in different ways. BERT uses an encoder-only structure with bidirectional attention and masked language modeling. GPT uses a decoder-only structure with causal attention for autoregressive generation. T5 causal attention for autoregressive, that's here. T5 keeps the full encoder-decoder design and frames everything as text-to-text. Vision transformers apply the same encoder idea to image patches, and models like reformer and longformer modify attention patterns to handle very long sequences efficiently. Okay, final part of this page, and this reads, okay. The impact of this architecture is hard to overstate. Parallel computation, strong handling of long-range dependencies, and clean scaling behavior made transformers the default choice across language, vision, and multimodal systems. Once you understand this structure, models like GPT, BERT, and many others become variations on a single coherent theme. Yes, let's see what is next. Variance and optimizations. Okay. Now, let's push forward and talk about why attention needed all these variants in the first place. So, standard self-attention is powerful, but it comes with a real cost. The moment your sequence length grows, computation explodes. That's not a theoretical annoyance. And it becomes a hard bottleneck in practice. Okay, so look at here. In standard self-attention, time complexity scales of O of n squared times d, and where n is the sequence length and d is the model dimension. Space complexity is O of n squared because we explicitly store the attention matrix. So what is the problem? If n is small, this is fine. But once you move to long documents, genomic sequences, or high-resolution images, the quadratic term dominates everything. And this is where efficient attention mechanisms come in. The goal is simple: keep as much of the modeling power of attention as possible while reducing compute or memory. Different variants make different trade-offs. Look at linear attention takes an approximation approach. Instead of computing the full softmax attention matrix, it uses kernel methods to reorder operations. That drops complexity closer to linear in sequence length. The trade-off is accuracy. You gain efficiency, especially for every long sequences, but you no longer compute exact attention. 2. Sparse attention goes in a different direction. Rather than approximating attention everywhere, it restricts which positions are allowed to attend to which others. You define a sparse pattern that could be local windows, strided connections, or a mix of both. Complexity drops to something like O of n times W or O of n log n depending on the pattern. Low rank attention factorizes the attention matrix itself. The idea is that the full attention matrix often has lower intrinsic rank than its size suggests. By exploiting that, you reduce parameters and computation while keeping strong performance on many tasks. And flash attention takes a completely different angle. It doesn't change the math at all. Instead, it reorganizes computation to match GPU memory hierarchies. By tiling to computation and performing softmax in blocks, it minimizes expensive memory reads and writes. The result is still O of n squared, but 2 to 4 times faster in practice. Okay. Now, let's look at sparse attention patterns visually. What's happening here? Full attention means every query attends to every key. That's the dense triangle you see here. Local attention restricts each position to a fixed window around itself. Strided attention lets each position attend at regular intervals. And global plus local attention introduces a small set of global tokens that attend everywhere, while most tokens stay local. Okay, and here boxes here. With local attention, each position attends to nearby tokens within a window of size W. Okay, and complexity becomes O of NW. This works well for text with strong local structure, where nearby words matter more than distant ones. Strided attention attends every kth position. Complexity drops to O of n squared over k. This pattern is good for capturing long-range structure with regular spacing. Global plus local, look at here. Global plus local attention combines both ideas, as you can guess. Most tokens use local attention, but a few global tokens attend across the entire sequence. Complexity becomes O of NW plus NG, where G is the number of local global tokens. This pattern is used in models like Longformer for long documents. And let me check. Okay. Random attention assigns each position a random subset of attention targets. Complexity becomes O of NR, where R is the random set size. At scale, this surprisingly preserves connectivity across the sequence and works well for large pre-training setups, as seen in Big Bird. Yes. Now let's switch gears to cross attention. Cross attention allows one sequence to attend to another. This is essential in encoder-decoder models, multimodal systems, and retrieval-based architectures. And equation is here. Let's read. Read because understanding. Okay, not just look here. the equation here is cross attention of Q sub A, K sub B, V sub B equals softmax of Q sub A, K sub B transpose divided by square root of D sub K times V sub B. So here queries come from sequence A, while keys and values come from sequence B. And what are the applications? Look at that. In machine translation, the decoder attends to encoder representations of the source sentence. In image captioning, text attends to image features. In question answering, the question attends to document passages. The multimodal models like Grip or Flamingo, text and image attend to each other. And for multidimensional data like image, axial attention becomes useful. Instead of applying attention across the full two-dimensional grid, the axial attention factorizes it. So you apply attention along rows, then along columns. For two-dimensional data, this reduces complexity from O of n squared to O of n times square root of n. Okay, and here you can see a single pixel first attending across its row, then across its column. Together, these two passes allow information to propagate globally without paying full quadratic cost. Okay, here, next. Relative positional attention. Instead of encoding absolute positions, relative positional attention directly models distances between tokens. And equation is here shown like that. Attention sub ij equals softmax of q sub I k sub j transpose plus q sub I r sub ij transpose divided by square root of d sub k. Here r sub ij represents a learned relative position embedding for offset j minus I. Okay. And this approach generalizes better to longer sequences, produces more interpretable patterns, and works especially well in domains where relative distance matters more than absolute position like music or code. And GQA or grouped query attention, that's a very practical optimization, grouped query attention. This is used in models like Llama. Okay, Llama 2. So let's look what's happening here. In standard multi-head attention, you have H query heads and H key value heads. You know that. And in multi-query attention, you keep H query heads but collapse key value heads to 1. Grouped query attention sits in between. You keep H query heads but use G key value heads where G is smaller than H, for example H divided by 8. This dramatically reduces memory usage during inference. Look at flash attention. That deserves one more mention here. By minimizing memory traffic between GPU high bandwidth memory and on-chip SRAM, it enables longer context windows and faster training without approximations. That's why it's become standard in modern large-scale models. So how to choose right attention variant? First, consider sequence length. Okay, standard attention works well up to a couple thousand tokens. Beyond that, sparse or linear variants become attractive. Next, think about the task. Ask, do you need bidirectional context or causal generation? That determines masking. Then consider your compute budget. Memory constrained setups benefit from grouped query attention or sparse patterns. And finally, look at the domain. Images benefit from axial or windowed attention. Multimodal systems rely on cross attention. Okay, 5 is done and 6. So, attention didn't stay confined to machine translation for very long. Once people realized it could model complex relationships directly, it started showing up everywhere. In NLP, attention is the core engine. In language modeling, models like GPT and Llama use causal self-attention to predict the next token. Why causal? Because during generation, you are only allowed to look backward. That single constraint is what enables text generation, completion, and few-shot learning. In machine translation, this is where the original transformer made its mark. Encoder-decoder attention aligns source and target sentences, letting the decoder focus on the right source words at the right time. In question answering, models like BART use bidirectional attention, meaning every token can attend to both left and right context. And that's what allows the model to understand questions and locate precise answers in passages. And for summarization, attention highlights salient parts of the document and surpasses noise, which is how we get concise summarizes that still preserve key facts. Okay, sorry for my voice. And that's okay. And tasks like named entity recognition and sentiment analysis benefit for the same reason. Attention lets the model weight context dynamically instead of relying on fixed windows. Okay, and computer vision. The big shift here was treating images as sequences. Okay, in a vision transformer, the image is split into patches, and each patch becomes a token. Those patch embeddings, along with a special CLS token, are fed into a standard transformer encoder. The model uses multi-head self-attention to learn spatial relationships directly with enough data with is there any here with I mean vision transformers match or exit convolutional networks, even though they don't bake in locality or translation invariance by design. Okay, and the key idea is that attention can learn spatial structure on its own. In object detection, models like DETR use attention to perform set-based prediction, eliminating handcrafted components like anchors, boxes, and non-maximum suppression. For image segmentation, what can I say? Attention provides global context, which helps define object boundaries more clearly. In image generation, diffusion models rely heavily on attention to maintain global coherence while generating fine-grained details. And for video understanding, spatio-temporal attention captures relationships across both space and time. Look at that. Attention really shines once you combine modalities. Cross-attention between text, image, audio, and video enables models that can understand and generate across domains. In CLIP, attention helps align text and image representations in a shared embedding space, enabling zero-shot classification. In DALL-E, cross-attention in the decoder maps text tokens to image features to generate images from prompts. Flamingo uses gated cross-attention layers to inject visual information into a language model. Okay, and here whisper, and what we can say for whisper. Whisper applies encoder decoder attention to map audio to text for speech recognition and translation. Image bind extends this idea further, learning a joint embedding space across 6 modalities. Yes, and attention has also made a major impact in science. AlphaFold is a flagship example here. AlphaFold uh, uses attention to model relationships between amino acids, incorporating evolution signals and physical constraints. Okay, and the Evoformer module applies triangular attention to reason about protein structure in three-dimensional space, reaching atomic level accuracy. In drug discovery, attention models molecular graphs to predict binding affinity and toxicity. In genomics, attention identifies regulatory elements and predicts gene expression. Climate modeling uses spatio-temporal attention to capture atmospheric dynamics. Materials science applies attention to atomic structures to predict properties and design new materials. Okay, and here in speech, attention-based models like Conformer combine convolution with self-attention for state-of-the-art recognition. In text-to-speech models like Decathlon to use attention to align text tokens with acoustic frames. So, and music transformers relies on relative position attention to generate long-range musical structure. And audio classification uses self-attention or spectrograms to classify sounds and acoustic scenes. And yes, reinforcement learning is my another area. So, attention even shows up in reinforcement learning. Decision transformer reframes reinforcement learning as sequence modeling. States, actions, and rewards become tokens. Self-attention over trajectories enables long-term credit assignments without the instability of traditional value-based methods. In multi-agent systems, attention allows agents to coordinate by selectively focusing on other agents. In game playing, models like AlphaStar use attention over game states for strategic decision making. In game playing, models like AlphaStar, we talk about here, and in robotics and autonomous driving, spatio-temporal attention fuses sensor streams and action histories to improve control and perception. And GNS for graph attention networks or GATs here. Another neural networks type that I like. Anyway, here, graph attention networks assign attention weights to neighbors dynamically instead of treating all neighbors equally. Look what's happening here. Alpha sub ij equals softmax of leaky value of a transpose times the concatenation of wh sub I and wh sub j. And here leaky value. The updated node representation h prime sub I equals sigma of the sum over j of alpha sub ij times wh sub j, where sigma is here, that's sigma. And this lets the model learn which neighbors matter most. Applications include social networks, knowledge graphs, traffic prediction, and molecular property prediction. Okay, and here brings this back to implementation. Sorry, first social networks, other things. Okay, now implementation is here. Now, plot time. And understanding how attention works in code matters because small details have big effects. Let's begin. We import torch and math. Okay, the class scale.product attention inherits from NN module. In the initializer, we store d sub k, pronounced dk, and define a dropout layer. And in the forward pass, we receive key, q, and v along with an optional mask. The first step is computing attention scores. That's torch dot mathmul of q and k transpose divided by square root of the key. This scaling term is important because without it, dot products grow large as dimensionality increases, which pushes softmax into saturation. And masking part. If a mask is provided, we apply it by filling masked positions with a large negative value, -1e9 pronounced, -1 times 10 to ninth. After softmax, those positions get near zero probability. So next we apply softmax along the last dimension to obtain attention weights. Dropout is applied for regularization, and we compute the weighted sum of values by multiplying the attention weights with v. The function returns both the output and the attention weights. Okay, scale.product attention, and multi-head code block is here. Just example. And we import torch and torch.nn, same as before. Then we define multi-head attention class. In the initializer, notice the first assertion. We explicitly check that D model is divisible by the number of heads. Why do we care? Because each head gets an equal slice of the model dimension. If that division doesn't work cleanly, the whole idea of parallel attention heads breaks down. We store the model num heads and then compute d sub k as d model divided by num heads, and this dk is the dimension to each head will operate on. Then we define three linear layers, wq, wk, and wv. These project the input into queries, keys, and values, but still at a full model dimension. We also define wo, the output projection, which mixes information back together after all heads are combined. Notice that we reused the scaled dot product attention module from earlier. That's intentional. Multi-head attention is not a new attention mechanism. It's the same attention applied multiple times in parallel on different learned subspaces. Jump to forward pass. We grab the batch size from Q, then we apply the linear projections to Q, K, and V. After that, we reshape. This view co-splits the model dimension into num heads and dk, and then we transpose so the head dimension comes before the sequence dimension. Here, this arrangement is important. It allows each head to attend independently. Okay, and once that's done, we apply attention. The output X has one result per head. Then we reverse the earlier reshaping. We transpose back, call contiguous to make memory layout safe, and reshape to recover original D model dimension. Finally, WO mixes the heads together and dropout is applied before returning the output and attention weights. So the key takeaway here is that each head can focus on different patterns. One head might lock onto positional relationships. Another might focus on syntactic structure. Another might track long-range dependencies. All of that happens in parallel. And Here, strategies. We'll talk about for this because even a perfect implementation can fail without the right setup. Okay, transformers are sensitive to learning rate. In practice, you almost always use warm-up followed by decay. Early on, you slowly increase the learning rate so the model doesn't destabilize. After that, you decay it, often using inverse square root decay. If training blows up early, learning rate is usually the first thing to check. Gradient clipping is another safety mechanism. By clipping the norm, typically around 1 or 5, you prevent rare but destructive gradient spikes. Label smoothing comes with our confidence. Instead of assigning probability 1 to the correct cluster, you spread a small amount of mass, often epsilon equals 0.1, pronounced epsilon equals 0.1 across the vocabulary, and dropout is applied not just to activations but also attention weights and residual paths, and the exact rate depends on dataset size. Okay, hyperparameter selection. As models get larger, everything scales. Model dimension increases, number of heads increases, feed-forward dimension grows, and depth increases. Dropout tends to stabilize around 0.1 for larger models, while learning rates usually decrease as model size grows. These rates are not arbitrary. They are the result of a lot of painful trial and error across many teams. And now optimization techniques. Mixed precision training is almost standard now. You run forward and backward passes in FP16 while keeping parameter updates in FP32. That alone can cut memory in half and significantly increase throughput. Gradient accumulation is how you simulate large batch sizes when GPU memory is limited. You accumulate gradients across steps and update less frequently. Gradient check pointing traits compute for memory by recomputing activations during the backward pass. And efficient attention kernels like flash attention fuse operations to reduce memory movements and speed things up dramatically. Okay, of course, things can still go wrong. Now, one classic failure mode is exploding or vanishing gradients. You will see loss turn into none or training completely stalled. Then, when that happens, reduce the learn rate, check gradient clipping, and confirm layer normalization placement and weight initialization. Another issue is attention collapse. All attention mass concentrates on a single token, often the first one. When you see that, increase dropout on attention weights, which switch to pre-layer normalization and check numerical stability in softmaxed. Okay, and long sequences introduce their own problems. Models that work fine on short inputs may fail badly on longer ones. Solutions include relative positional encodings, sparse attention patterns, curriculum style increases in sequence length, or switching to architectures designed for long context like Longformer or Big Bird. And debugging and visualization help a lot here. Plot attention weights as heat maps. You want to see structure, not noise. Look for syntactic patterns in early layers and semantic patterns in later ones. Visualize different heads separately because averaging too early can hide useful behavior. Tools like BARTviz and Attention Flow make this interactive and much easier to reason about. Okay, final part of this video. Production considerations. Now, batch size tuning matters for throughput, but it often requires learning rate adjustment. And quantization, especially INT8, can shrink models dramatically with minimal accuracy loss. Pruning removes less useful heads or layers. Knowledge distillation trains smaller models to mimic larger ones, preserving most performance with far fewer parameters. And for autoregressive models, caching key value pairs avoids recomputation and can cut inference cost roughly in half for long sequences. And before shipping anything, always benchmark. Compare training speed, memory usage, and final performance against known baselines. Profiling tools will usually show that optimized attention implementations are not just a little faster, but sometimes an order of magnitude better than naive ones. Okay, at this stage, attention should not feel abstract anymore. You have seen how it's built, how it scales, how it breaks, and how to fix it. Okay, and that's all for this lesson. Thank you for listening.